Hi, I'm David Eppstein, and this is New Results in Sona Drawing, Hardness and TSP Separation. This work has many co-authors who came together to work on it during a virtual workshop on computational geometry, originally intended to be the 35th Bel Air's Winter Workshop on Computational Geometry, organized by Gottfried Toussaint and Erik Demaine. We would like to dedicate this work to Gottfried, who inspired us in it and in many other ways. The Chokwe people of southwestern Africa have a tradition of making decorative patterns called Sona or Lusona, in which dots in a grid-like arrangement are separated from each other by a self-crossing curve, drawn as a single stroke. These patterns may be used for children's games, as a mnemonic device for telling stories, and as a decorative pattern in the crafts of the Chokwe people. The people of South India have a similar drawing style known as Puli Kolam in Tamil, and by other names in other languages of the region. In this part of the world, it's traditional for the women of the house to draw these patterns daily using rice flour on the thresholds of their homes. Gottfried brought these drawings to the attention of the computational geometry community in 2005 and participated in a 2006 CCCG paper with 12 other authors that formalized their mathematical principles, in some cases imposing more strict requirements on them than appear in the original artworks. This paper defined a Sona curve for a given finite set of point sites to be a single curve that closes up on itself in the plane and that intersects itself only at simple crossings where two arcs of the curve cross each other. It required the curve to stay disjoint from all the given sites and to surround each one within its own region, separated by the curve from all the other sites. Finally, it required the curve to avoid making extra empty regions. All of the regions formed by the crossings of the curve should contain one of the given sites. The 2006 paper also presented several results on these curves, including curves that turn only clockwise or that minimize the winding number, polygonal curves with a minimum number of straight segments, curves drawn in an integer grid, and curves of minimum length. It is these last two sets of results on grid and minimum length curves that we address in this work, solving several open problems from the previous paper. Many of the traditional Sona patterns have a grid-like structure, and the 2006 paper also addressed grid Sona drawing. It showed that if the sites are placed at the centers of cells of an integer grid, but then the grid is blown up by a factor of 3, it's always possible to find a Sona curve that follows the edges of the blown-up grid. The expansion factor is necessary. Some very simple dot patterns, such as 5 points in a quincunx pattern, have no Sona curve, and the 2006 paper asked for a characterization of which dot patterns have grid Sona drawings and which do not. We show that no nice characterization is possible, or at least that there's unlikely to be a characterization that can be implemented by an efficient algorithm, by proving that testing for the existence of a grid Sona drawing is NP complete. Our proof is a straightforward reduction from planar 3-sat, using tightly packed lines of dots as wires, and the placement of a grid Sona curve between them as signals on the wires. The main difficulty in the proof is arranging the gadgets in such a way that, for a satisfiable 3-sat instance, the pieces of grid Sona curve coming from each gadget can be connected together to form a single curve, satisfying all of the properties that we require a Sona curve to have. We also answer another open problem from the 2006 paper on the complexity of finding Sona curves with minimum length. Here, the NP completeness proof is even easier. Just take a hard instance of the traveling salesperson problem and replace every point by two close together points. The Sona curve must pass near each pair of points to separate them, and therefore the minimum length Sona curve has length approximately equal to the minimum length salesperson tour. But is it really reasonable to ask for a minimum length Sona curve? If you have a Sona curve that passes some distance away from every site, you can always stretch it tighter, bringing it closer to the sites and making it shorter. So mathematically, according to our definitions, there's no such thing as a shortest Sona curve. However, there always exists a shortest limiting length among all possible Sona curves. There exist Sona curves whose length is above this limiting length, but arbitrarily close to it. And there do not exist Sona curves shorter than this length. So when we talk about the minimum length Sona curve, this limiting length is what we really mean. Another equivalent way to define the shortest Sona curve length is to allow curves that pass through some of the sites instead of around them, as long as we can still assign sites to regions in such a way that each region gets one assigned site that's either inside it or on its boundary. Any curve of this type can be transformed into a proper Sona curve by adding a small detour around each site without significantly changing its length. This alternative definition shows in particular that the traveling salesperson tour is an upper bound for the minimum length Sona curve. The 2006 paper stated a result in the opposite direction. Any Sona curve can be turned into a traveling salesperson tour that is longer by a factor of at most pi plus 2 over pi, about 1.637. They didn't detail the proof, but it's easy. To form a short TSP tour from a Sona curve, just detour from the Sona curve to each site along a shortest connecting line segment and back. The bound on the length of the TSP tour that you get from this detouring process follows from the isoparametric inequality. This naturally raises the question of whether there can exist examples of sets of sites for which the traveling salesperson tour and Sona curve are this far apart. We provide a nearly tight answer in our paper. To find sets of points whose Sona and TSP lengths are well separated, we exploit a basic fact about the TSP, connecting it to the theory of circle packings. If we have a collection of disjoint circles in the plane, then the length of the TSP of their centers is at least the sum of diameters of the circles, because that's the length required for the TSP to enter each circle, reach its center, and then exit the circle again. If we can find a collection of circles whose Sona length is much smaller than this sum of diameters, we can use their centers to separate the minimum Sona curve length and TSP length. We will find examples of circle packings that separate the traveling salesperson tour and Sona curve lengths by starting with an arbitrary Sona curve, using it to guide a circle packing, and then comparing the Sona and TSP tours of the centers of the circles. We can actually start with a more general system of multiple curves rather than just a single curve, and here we're using a system of two crossing rectangles. We place many tiny circles along these curves, and big circles centered at the Sona sites. The TSP length is lower bounded by the sum of diameters of these circles, which is more or less the same as the length of the tour that you get by detouring from the Sona curve to each site and back. On the other hand, it's possible to find a Sona curve for the system of centers of these circles that follows the original system of curves, making only small loops around the center of each of the tiny circles, with length more or less the same as the original system of Sona curves. So if we can find an arbitrary system of Sona curves for which the curve length is significantly shorter than the TSP tour derived from it by making detours, regardless of whether either of these two lengths are optimal for the given Sona sites, we can add more sites, the centers of the tiny circles, and produce an example where the optimal Sona curve and optimal TSP tour are very different. A large square grid gives a lower bound of 1.5 on the ratio of Sona and TSP length. But we can do a little better by adding fractal details to the grid, smaller rounded squares that surround each crossing of the outer level grid, even smaller rounded squares that surround each crossing of the first level of smaller squares, and so on. Our paper gives a messy closed form calculation of the resulting ratio, but it's approximately 1.548. In conclusion, we've shown that finding grid Sona curves is hard, and that finding minimum length Sona curves is hard, answering two open questions from the 2006 paper on Sona curves. We've also provided examples showing that the traveling salesman tour can be longer than the Sona curve for the same sites by a factor of at least 1.548, complementing the previous result that the ratio between these two is at most 1.637. Tightening these two bounds remains an open problem. Another open problem concerns grid Sona curves, which always exist when we blow up the grid by a factor of 3. What happens when we reduce the blow-up factor to 2? We leave these questions for future research.